Excellent. Well, Patrick, first of all, Patrick Weimer from Beavermatic, thank you for hosting the technical sessions as an organization. I'm going to stand here because maybe it's a little easier for me to see the slides along with you from that standpoint. There's a humorous aside here. I submitted 2 talks to MTI for presentation. One of them was a half-hour long, one of them was an hour long. This was the hour-long presentation. The one I'm giving tomorrow was the half-hour long presentation. Of course, they changed it. This is now the half-hour presentation, and tomorrow's is the 1-hour presentation. So I've taken my number of slides and chopped them exactly in half to make it a half-hour long. So we're not going to cover all the things in the introduction, but it would be my pleasure at any time, either when I'm around during the conference or at any time afterward, get a hold of me, contact me, ask questions, and we'll fill in the gaps. And I certainly would be more than happy to provide the full presentation to anyone who asks me for it from that standpoint. I want to also thank the Timken Company, who a number of years ago changed my attitude about this particular talk. I used to talk about quenching and controlling distortion. And I sat through a technical talk from a gentleman at Timken, and he used the word managing distortion. And his comment was, we can't control it, we can only manage it. So I think that's something we all have to be extremely aware of from that standpoint. But we're going to go over some of the basic aspects of it. Now, a number of years ago, in the mid and late 1990s, we turned around as an industry. ASM ran, the American Society for Metals ran a group of surveys of the industry. They surveyed the commercial heat treat industry, they surveyed the captive heat treat industry, they surveyed the supplier base, and they asked the questions, what is important in the industry? Where are we going in the 21st century? It was very appropriate. And as part of that work, Vision 2020 was created, if you will, as a document, as a goal, a guideline. Where will we be in 2020? Well, it's now 2012, rapidly becoming 2013, right? So the question is, how close are we? But what I've done is I've tried to summarize, listed in priority order, some of the aspects that survey came up with as the keys to heat treating in the 21st century. Interestingly enough, the first was the use of energy-efficient equipment. What I always thought was interesting about this is the fact that the survey revealed that energy was the #1 concern of our entire heat treating industry, and something that was not, users and customers were not willing to pay for energy efficiency. So I thought that was very interesting conclusion. But the second one, which really is the subject of what we're talking about today, is processing with minimal part distortion. So when we talk about managing distortion, this is an ongoing issue. We've been battling it for years. We will continue to battle it for years. But I want you to recognize that you're not alone. The entire industry is trying very hard to struggle with the issues of how do we minimize part distortion. Another survey, and I only list a couple, was the optimization of diffusion-related processes. The carburizing and carbonitriding, the nitriding, nitrocarburizing, even the boronizing processes and things. But you can see here, I'll let you read the rest of these for yourself, but this was a list from the survey of saying what was really important to us. And one of the things that I want everyone to realize is that we're working hand in hand with the scientific community to understand distortion. You're probably all familiar with the Ishikawa, or what we call fishbone diagrams, if you will, where what we're trying to do is look at all the factors that obviously influence what we call dimensional variability. We have to look at the pre-treatments. We have to look at the manufacturing steps, such as machining. We have to look at the material and the material contribution. We have to look at our hardening processes, if hardening is the process we're doing. We have to look at quenching, for example. and we have to look at all the post-hardening treatments that we're going through. One of the things about these diagrams that people don't fully understand is that we're not trying to represent this and all of these process variables in one fishbone. Each of these, there must be a pointer somewhere on here, maybe. Not sure, we'll try this. Come up. Well, whatever I did, I just killed the presentation. Let's try that again. Sorry about that. It'll teach me to wonder what buttons are all about. There we go, I think we're back. Very lucky, yes. Just keep hitting buttons, something good happens. But I'm not touching anyway. We'll go from there. But the key here is the fact that what people fail to realize is that each one of the categories listed on this Ishikawa diagram has its own fishbone. And then there's a fishbone for each of the factors or variables on that one. So if you look at, for example, under quenching, and we deal with part design, quenching method, equipment, type of quench, and the quenching variables, if you were to click on quenching variables, you would develop another fishbone diagram, which would now carry you deeper into the subject. So the idea is the fact that from a science standpoint, we're trying to understand what's happening. The issue is, of course, that it's difficult to match the science with the real world. And why is that the case? Because the ideal furnace doesn't exist, right? We not only have process-induced variables, but we have equipment-induced variables that affect the outcome. So we have to be very, very aware of that. When we also look at and start to break down what the sources of distortion are, you know, oftentimes what we concentrate on, if you will, is we concentrate right here. We concentrate on the heat treatment practices and procedures, right? What happens is the fact that our customers give us parts, and those parts are distortion-free, right? They give us the parts, and we heat treat them, and we give them back, and it's, oh my gosh, oh my darn, guess what's happened? You've destroyed my parts. You've warped and distorted my parts. And the focus is really on heat treatment. And what we try to do as an industry is educate our customers that really the sources of distortion start with the steel making process and how the steel is actually produced. Is it a silicon steel that happens to be a coarse grained steel? Is it aluminum killed or calcium killed steel, which is going to refine the grains? So we have to look at the steel. We have to look at the entire part manufacturing sequence to try to understand what the internal stress state of the material actually is. And then we have to concentrate on any of the transformation-induced stresses that we create, either from a design standpoint, from creating the part, the geometry we've chosen to use, the steel, not only its quality, its inclusion content, but also its hardenability, and we'll talk a little bit about hardenability. We have to look at the heat treat process we're actually running. Are we running conventional temperatures? Are we trying to maybe run slightly higher temperatures on some of our processes? We have to look at the type of quench media. I mean, ideally, we'd like to still cool everything in air if we could, right? That's the goal. Well, you'll see some examples where even that doesn't work at times. But if it turns out that brine quenching is a necessity for the type of material that we're dealing with and the part geometry we're dealing with, then we have to manage distortion in a brine quench. It'd be ideal if we didn't have to, but the reality is we then have to manage distortion in the type of quench media we're dealing with. We also have, besides everything we do in heat treating, we may have post-ops such as grinding that may give us post-transformation induced stress as well, and all of that contributes to the final distortion state. So what I'm trying to convey with this particular slide is the fact that it's a complex situation that we're dealing with, some of which we can control and some of which we can't. So when you look at distortion, we are the unlucky creators of the obvious distortion on a particular component, but yet we are not often responsible for that. So we start by looking at the obvious slide that says we have various quench media which are listed on the left. We have brine, we have water, we have polymer, we have oil, we have high pressure gas, we have molten salt, we have air, we even have furnace cooling medias, and we go as far as quenching speed from very, very fast quenches like brine to very, very slow quenches like furnace cooling. But yet our distortion usually follows in exactly the opposite path. The more severe the quench, the higher the distortion rate. The lower the quench speed, the less distortion that actually occurs. Now this is a very, very generic representation. We know, for example, in certain high pressure gas quenching applications and things of this nature that we can actually take and use high pressure gas to better control the distortion of certain components, and we'll talk a little bit about that. But in general, this is the pattern that we have to be aware of. Again, we're all familiar with this, depending on what we're doing and looking at. Again, if it happens to be a liquid quench, we're dealing with 3 stages of cooling. Just to remind everybody, we have the vapor blanket or the film boiling stage. We have the bubble boiling or nucleate boiling stage as a second stage, and then we have the convective stage. So if we're quenching into a liquid, if we're quenching into oil, if we're quenching into polymer, we're developing and we're going through all 3 of these stages. What's important is to understand that if we could control the second stage, the bubble or nucleate boiling stage, we could control distortion. But the problem is the fact that the heat transfer that goes on during the bubble boiling stage is uncontrollable, if you will. So as a result of that, it is very difficult to control that particular stage of quenching. Now there are certain technologies, and there are what we call contour or shape type quenches that can, for example, using intensive quenching in water that can control certain distortion states by addressing this idea of bubble or nucleate boiling, but I think this is significant. The other thing that I find from my experience out in the field is the fact that people understand the 3 stages of quenching, but then you start to look at the furnace loads that they've actually created in the quench tanks that they are actually using. And you find in many cases that the load makeup is such that they've actually taken and created a problem with distortion based on how they've loaded parts in baskets. And as commercial heat treaters, one of the challenges, of course, is that you want to maximize or attempt to maximize your furnace loading. At the same time, you have to try to keep the distortion rates to a minimum. So the other thing, besides the science of the 3 stages of cooling, is for everyone to realize that, at least in my view, the loading of baskets is one of the most significant aspects of contributing to the final distortion state of a product. I can't tell you how many times I've looked at multiple layer loading in baskets only to discover that, for example, the quench design of a particular unit is such that you can't remove the heat uniformly through all the layers of the basket, for example. So that's something that we have to be very, very aware of as well. This is a European study that was done a few years ago, and it's not designed to give everyone in the room a warm, fuzzy feeling, but it gives me a warm, fuzzy feeling. Someone actually analyzed and looked at the sources of distortion and actually found in this particular study a whopping 50 to 60% of the distortion was due to the design of the component, the design geometry of the part, the component shape. Another 20 to 30% of distortion was really due to material quality and hardenability. And our contribution to the distortion issue was a whopping 5 to 10%. Of course, in our customers' eyes, what's our contribution to distortion? 100%, absolutely. So, but there are some really compelling arguments to say that. And I want to talk about all these. One of the things that I thought was interesting was, and I should have put down source here, this is a picture that comes out of one of the ASM handbooks. And I've always been leery of pictures, if you will, but the gear wheel on the left is showing that the particular design and placement of the holes turned around and contributed to the warpage of the gear teeth. Everybody see that? The solution, if you will, was to redesign the gear, again having similar weight reduction, only using smaller holes in a different pattern, and lo and behold, the teeth don't distort. I've looked at this picture for years and years and said, you know, I'm not so sure that exists in the real world. And I was at a client, not too recently, but at a client, and I happened to look at the placement of that hole in relation to the gear teeth. Do we stand a chance of keeping those gear teeth from distorting with the way that hole is placed? We're dead. We're dead in the water before we start. So the message here is the fact that sometimes our customers do things, unwittingly of course, that really contribute to the distortion state. And we as heat treaters, we want to be proactive rather than reactive. We want to turn around and we want to say, look, if we're receiving a part like this, one thing, the only thing we're going to guarantee you is we're going to do what? We're going to distort those gear teeth, especially if we're quenching in oil or something like this. If we were gas quenching, if we have enough hardenability in the material, we might stand a chance with this. But chances are we're not going to. So realize that design is one of the aspects that we can't totally control, but we can contribute to it. One of the other things I find is as I go throughout the industry, and now I've had the privilege, by the way, of being the consulting metallurgist for MTI, and now I'm getting an awful lot of calls from members talking about real world problems that they're experiencing. And one of the things that I find is the fact, and this is something I've talked about for years, but no one is paying attention, or very seldom do we pay attention to the hardenability of the material. We don't necessarily factor that in. I don't want to embarrass anybody by show of hands to say, when you go to run a load, how often do you have the material certification sheet to review? How often do you take a look at the hardenability of the material, whether the DIs are calculated or they're not, or the geometry values are listed or they're not? But the idea is the fact that we want to use the lowest hardenability material we can that will still achieve the core hardness, but at the same time we want to take and realize that higher hardenability materials are more distortion prone. So we have to pay attention to that. Also, many times the solution, if you will, is to stress relieve the material at some point during the manufacturing process. Well, there's an example of a load that happened to be a stainless steel, and they did a quick stress relief on these plates, and what did they find? An awful lot of stress in those plates, right? So if you had thought this through, if you were then going through a hardening process, you would see a significant amount of distortion. So as a result of that, sometimes we say that, you know, stress relief is a good thing because it will help not only negate the stress from steel making, but it will also result in less distortion after we heat treat. But sometimes there's so much stress built up in the material that we don't stand a chance before we even start. So you have to realize that stress relief is a good thing, but at the same time you have to worry about the internal stress of the material. This applies a little bit to just my general philosophy, but gears in particular. You know, if we were in the real estate industry and I were sitting up here talking about housing or something, the three words that I would say is what? Location, location, location. Well, to me, in the gear industry, my three words are normalize, normalize, normalize. Costs money to normalize, but at the same time, normalizing, besides improving chemical homogeneity, is going to definitely improve and give you a much more stable part, and it will turn around and properly prepare that part for success when we heat treat. The thing about normalizing is the fact that oftentimes we don't do the job correctly. We heat the temperature, we don't give it, you know, the standard rule in the heat treat industry is what? 1 hour per inch of cross-sectional thickness. We all know it, we all love it. Did anyone ever wonder where that rule came from? Or 1 gallon per pound of steel when we oil quench? Well, you'll have to read an upcoming heat treat Dr. column for the answer. But I was curious about that. That is a real plug, isn't it? But I'm curious about the little questions, if you will, which are really big questions. But the idea, and I do have the answer. I have found the answer, but I'm not going to share it. I'm kind of jealous. I'm going to raise the expectation level in the room. But the idea here is the fact that normalizing, we should have a minimum of a 2-hour soak, okay, irrespective of the thickness of the material. The material might be 25 millimeters thick or 1 inch thick. We still want to soak it for a minimum of 2 hours. Now, if it's 100 millimeters thick, if it's 4 inches thick, we want to soak, if you will, 1 hour per inch, 2 hours minimum from that standpoint. But we want to soak long enough to achieve a very uniform temperature, and we want to take and we want to cool as slowly as possible, or as uniformly as possible, excuse me, so that we get the true effects of normalizing. It's really a good way to stabilize. The other things we have to worry about, and this depends if it's an atmosphere furnace as shown in this example, or if it's a vacuum furnace, but we have to worry about either the effects of heating rate or the ramp rate on the material, which is a big portion of that as well. What I often find is the fact that when we have extremely dense loads like the one shown on the right here, what happens is the fact that we know we're going to get a temperature variation on heating, correct? Between the outside of that load and the inside of that load, irrespective of the fact if we have a circulating fan or we don't have a circulating fan. That's an extremely dense load. Those happen to be torque converters, but an extremely dense load. So we have to make sure that we have adequate time to develop the proper temperature uniformity within the load. And then we have, of course, the selection of austenitizing temperature and what we want to deal with it. And as we all know from a hardening standpoint, we have a variety of different hardening temperatures. And which hardening temperature is preferred, and many times, especially in deep case carburizing, we want to try to push that as much as we can from that standpoint. So we have to pay attention to the effects of austenitizing and also the effects of soak time. If it's carburizing, for example, too short a soak time gives us a shallow case depth, mixed microstructures. If it's too long a time, we're turning around and maybe getting issues where fixturing or other factors can cause high temperature creep and contribute to the distortion state as well. So these are some of the process parameters we have to look at. Why manage distortion? I gave another gear example here because if the gear teeth are to distort, then when we go to grind the gear teeth, we're actually grinding away the best part of the case. So we're trying to develop high hardness above 58 Rockwell C, and yet if we're not careful, if the gear teeth have distorted, we're going to grind right through the case we've put on and ultimately have a poor performing gear. I'm not here to say that one manufacturer's equipment is better than another manufacturer's equipment, or new equipment is better than used equipment, etc. But I am saying that you want to be careful to select the proper piece of equipment to do the job, and to me that's critical to to managing distortion and minimizing residual stress. And again, the maintenance of the equipment is very critical to the whole process as well. I can't tell you, and I'm going to kind of end at this point because there's still X number of slides that follow, but I can't tell you how many times that the distortion of parts is so influenced by how we maintain our systems. I was at an organization, and I won't name who, but we took an integral quench furnace, and we drained all the oil out of it, and we took out 55 gallons worth of, 55-gallon drums worth of sludge out of the bottom of the tank. I mean, how effective was the oil quenching going on in that particular? We actually found parts that were serial numbered to 1977. I'm not kidding you. This is true. So the message here about managing distortion is the fact that there are a whole bunch of factors, and they're very individual to your operations that you run. But taking and following basic rules, working with your customers, keeping your equipment in good operating condition, and watching the loading is really key. And at that point, I think, as I said, I'll power this down and then just ask any questions if I could.